Så er jeg på. Hello and welcome. Can you hear me? All right. Ulrich, who normally teaches in this auditorium, is at a course this week. And this is why I teach the course. Normally I teach general engineering in auditorium 42. No, 43. And so it will be in English today. If you want to have it in Danish, there are a couple of videos that you can watch. And I will be happy to answer questions in Danish in the break. But the lecture will be in English. And this is the next to last genuine lecture. Oh, that will be the one on Friday. The last one about Stokes' theorem will be after the project work, which starts right after Easter. So we are about to finish the course in mathematics. So, but what I'm going to tell you today is rather important. Many of you can use this in your project work, so I think you should pay some attention to this, and especially you should work with the exercises this afternoon. So the talk today is about flux integral and about Gauss's theorem. So what I'm going to do, or the agenda, we have the flux integral. So I'll start about talking about this. It's also called the orthogonal surface integral. Then I'm going to talk about Gauss's divergence theorem. Divergence theorem. And this will be for a closed surface. Then I'll talk about the divergence theorem. For an open surface, or use Gauss's theorem for an open surface. And then finally I'll talk a bit about volume expansion. And if you look at the exercises this afternoon, then if I write here, exercises, then exercise 1 and 3 is about the flux integral. And then the divergence theorem, it's number 4, 5, and 6. And then finally, there is an exercise about volume expansion. Volume expansion is in the E note mainly used theoretically in order to make a foundation for Gauss's theorem. So, but there is an exercise about it, so I'll tell you a bit about it. Now, let's try to motivate this flux integral. let's say we have a window. We have a window here. We are looking at the window from the side. And then you have a vector field. Typically, it will be sun rays. And what you could be interested in is to see, well, how much is actually radiated through this window. And in order to do so, we need to define a direction of the surface. That is, we need to find a unit normal vector to the surface. And then you can see if we have such a vector here, the thing that matters is the projection of this vector field onto the normal. So if at any point on the surface here you take the normal projection, or the projection to the normal, then you can see how much goes through it. And I write it in this way. You see the projection is the vector field times, or dotted with the normal vector. Then you have this projection. And what you then do is that you sum it up. You sum it up all over this field here. So if I call this field F, then this is simply the flux integral. So, yeah?
What do you mean by how much goes through it? Like how much it passes the line?
Yeah.
What do you mean?
Yeah, yeah.
That's what.
Yeah.
Okay.
So, this is actually the flux integral. And let's see here. Now I'm going to interpret this flux integral as a double integral. So let me draw a surface here. This is a surface. And I call this FR. And you have a vector field, and given with the 3 coordinate functions. And each of these components or coordinates, they are given as functions from R3. That is, this vector field is defined everywhere in space. Also, you have given a parametric representation of this surface here. Let me just, well, I could take this here. You have x, y, z, and you describe your surface in that in that coordinate system. But also you have your parameter space, and that is, you have an axis parallel rectangle like this, and this is mapped through your parametric representation. I have the parameters u and v. So this is given. So you have your vector field. I can draw a couple of vectors here. But also you have an orientation of your surface, and that is you have a normal vector. And so I just write down the parametric representation. It is given by these three coordinate functions, x, y, and z. And u is running from A to B, and v is running from C to D. Now the surface normal vector, or a unit normal vector, you get by making this cross product. You differentiate your representation with respect to u, you cross it with your parametric representation, differentiate with respect to v, and then you get a normal vector. And you need, in order to unfold this flux integral, you're very quiet, I guess, since the light is vanishing. I don't know. But you need to divide this by the length of the normal vector to get the unit normal vector. So this is the setting. You have parametric representation for the surface, and you have your flux or your vector field. Okay. And then I'm going to define it. We write it in this way. The flux of a vector field with respect to a surface. Here I call it the surface F. And I use R here to indicate that you have a parametric representation for this vector field. Now, this was the definition of the flux. And what we're going to do now is that we write this as a double integral. You integrate from A to B and from C to D in your parameter space. And then you have the restriction of the vector field to the surface. And you do that by entering the parametric representation into your vector field. Then you dot it with your normal vector. I have written it up here, so you will have this vector here divided by the length of this vector. Like this. And then, as ever, you multiply with the Jacobi function. The Jacobi function, and this is for this parametric representation, and it's a function of u and v, and then you integrate with respect to u and v. So this is the result. And then you have to remember what is the Jacobian for such a surface integral or such a representation. And it is simply just the length of this cross product. That is this one here. And this is truly nice because if you enter this into the integral formula here, then you can see that these two terms cancel, and you end up with this rather simple, but you end up with this formula A, B. You have V and then R of U and V. And then times this cross product. And I put a parenthesis here so you can see what the dot product, what the factors in the dot product are, and then du dv. So this is say flux integral written as a normal surface integral. So let us take an example. An example, we have a cylinder and we are looking in particularly on the curved surface of the cylinder. So let me draw this. See if I can do that. I just take this cylinder here, and then we have a normal x, y set, say like this, coordinate system, and you have the cylinder height, and then you have the radius of the cylinder is r. Now, the parametric representation, maybe I can write it here, UV, is, well, you are on, and we're looking at the curved surface, so say if you have a vector describing this, and you use the angle from the xz plane to this vector, then this vector for a point on the surface is r cosine u r sine u, and then some say set function here. And this means if you use, for set, you use the parameter v, then you get this parametric representation, cosine u, r sine u, and then v. And if you look at the parameters, u should be in this interval from 0 to 2 pi, and v should be in this interval from 0 to h. So this is simply a parametric representation of this curved surface. Now, let me find a normal vector to this curved surface. We take the derivative with respect to u, you get minus r sine u, and then you get r cosine u, and you get 0. And then the other parameter are this one. Here it's only the third coordinate function that depends on v, so you get 0, 0, 1. Now, when I take this, I have to take this out, and then I can get r cosine u for the first coordinate. And if I take these two out, then I have this cross product minus this one, and since it's the second one, it should change sign. So this will be this one, and then a 0. And that makes sense because you can see you have this cylindrical surface, and then you have the position vector to a point on the surface, and the normal vector is simply the same vector. It's parallel to that, same length. So this is the normal vector. Now I'm going to take a simple example. And I'm going to use this vector field. It's a constant vector field. And I get the flux out through this this curved surface, and it will be. Well, I'd better change to the next. So let me take this down. So let me write down the flux here. The flux of the vector field with respect to Fr. This is the integral from 0 to h, and then from 0 to 2 pi. This is the parameter interval. And then I should have the vector field, which is this constant vector field, 1, 0, 0. And then I should dot it with my normal vector, which is r cosine u, r sine u, du dv. So, and when you perform this, you get 0 to h, 0 to 2 pi, and then you simply get the first coordinate here, r cosine u, and then du dv. And you can see that this doesn't depend on v, so you can immediately perform the v integration, and you get a h, and you can put r outside the parenthesis, or outside the integration sign, or integral sign, and then you end up with the integral. And this is in fact 0. The integral is sine of u, and taking between these two limits it's 0, or it's 0 at both places. But whenever you have a trigonometric function or a periodic function and you integrate over a period, you get 0. So this is simply 0. Let's see if we can interpret this in a sense. Because what I'm going to do now is that I'm going to look at this cylinder from the top. So let's say we have our x, y coordinate system here. And the z coordinate is pointing out of the surface, perpendicularity. And then you look at the cylinder and it looks like this. And then you have your constant vector field here. It's pointing in that direction. And if you look at a point here, then you have the normal vector pointing in that direction. So if you take the projection of your constant vector field onto this normal vector here, you get this value. It's negative because it's in the opposite direction as a normal vector. But if you go on the opposite side here, then you have your vector field in that direction. And if you then make the projection down to the normal vector, you get the same numerical amount as this projection, but then it's positive. So whenever you have a negative contribution, you have a positive contribution. And when you then sum all these contributions, as you do when you make the integral around the circle, then you get a negative contribution for this side, and this cancels this positive the contribution from the other side. So this is the reason. Let me take another example. You have this vector field here, x, y, z. It's called the explosion vector field because when x and y gets larger, you get an outward pointing vector field that becomes larger and larger as you go out in space. Now again we look at the flux through the curved part of the cylinder. Let me write this down. Flux of this new vector field here, the explosion vector field, and through this surface. Again, you get the integral from 0 to h and from 0 to 2 pi. These are the parameter ranges. And then you get your vector field, and now you have to replace x, y, and z with your parametric representation. And remember, you had r cosine u, r sine u, and then finally for z you get this v here. Again, you should multiply this by the normal vector, and we computed that as r cosine u, r sine u, and 0. And then you should integrate with respect to u and v. And now if you do this dot product here, you get r squared cosine u squared and then you get r squared sine squared, and then finally v times 0, that is 0. So this is the result, and you have to integrate this. Now remember that cosine squared plus sine squared is equal to 1. So if I put r squared outside a parenthesis, then I get that this is simply 0 to h, 0 to 2 pi, and then r squared, and then du dv. This is a constant. I can take it outside the integration. And then I integrate a 1 over these intervals, so I get 2 pi times h. So this is how you normally compute flux integrals. But in certain cases, you can use a theorem that is rather important. This is perhaps some of the finest thing you see in this course, the theorem. And I'm not going to prove the theorem to you in detail, because we don't have time for that. But what I will do is that I will give you a hint of a proof, so you more or less accept what the result is, hopefully. But I'm going to start by, just keep it. So I'm going to start by telling you what Gauss's theorem is. Say we have a solid. I depict it in this way. It could be, whatever. And it is defined with a unit normal vector, and we are given the usual coordinate system. And I call the solid for omega. And this solid has a closed surface. And I write this because this is of importance. Closed surface. And then we are given a vector field with the three coordinates, v1, v2, and v3. And these are functions of x, y, and z, and it applies everywhere in space, this vector field. And we can compute the divergence of this vector field. This is simply the x derivative of the first coordinate plus the y derivative of the second coordinate plus the z derivative of the third coordinate. So this is simply a function. It's not a vector, it's a function from space into the real lines. It's a real function. This is the setting, and here comes Gauss. The space integral, or volume integral, of the divergence, this is a function of all the variables, over the solid, is equal to the flux of the integral with respect to the boundary of this solid, that is the surface of the solid. This is Gauss's theorem. And what I'm going to do now is that I'm going to make this plausible for you, and perhaps make it easy to remember by applying this or demonstrating this for a simple volume. So What I have here is that I have a volume that is bounded by a graph surface. Let me draw it a bit bigger. So it looks something like this. And then I have, say, a lower boundary. That looks something like this. So this is, say, the upper surface of my volume, and this is the lower surface of the volume. But then you can imagine that you have the whole field between these two surfaces, and this is vertically. So the side walls here in my volume, they are vertical. And let me just take, say, I could draw here. I think I will do that. If I do it like this. So what I have here is that I have my y-axis. I have here the z-axis, and here I have the x-axis. So I have in the xy plane, I have a parameter space. I have a parameter space that should be parallel to these coordinate lines. But here it goes from A to B, and here it goes from C to D. In order to make this demonstration, I am looking at a very simple vector field. It's a vertical vector field, and it is, of course, then 0, 0, and then the third component depends on z. So this is the vector field. The upper surface here, I call this F2, and the surface down here, F1. This is given by this equation. I have that the z-coordinate is a given function, g2 of x and y. So it's a normal height function for this surface. And similarly down here we have another, I should write that z is equal to g1 of u comma v. Let me continue by writing the divergence of v. Since this is 0, then the derivative with respect to x is 0 plus 0, and then you get dv3 dz. But since this only depends on z, I can write it as in this way here. So this is the third component. What I need now is I need a couple of parametric representation. I need a representation of my solid, and the solid is simply the field between these surfaces, and then I need parametric representations of the two surfaces. So let me write these representations down. And I use x as a parameter, the parameter u, and I use y as the parameter. And then you have any point in this rectangle here. So I say that the parametric representation for the solid, and it's a function of uv, and then I use w as the third parameter, is simply u, comma v, comma w, with where u runs from a to b, v runs from c to d, and then finally w runs from g1 of u comma v to g2 of u comma v. That is simply between this surface here and this surface. I need a parametric representation of the two surfaces. I get for F1, that is the lower surface, and it's a function of only u and v being a surface. And this is equal to, again, u comma v. And then the third coordinate is g1 of u comma v. And u is from a to b. And v is from c to d. The last one is quite similar. But here you get g2, of course, and the same parameter space. So this is the setting, and what I'm going to do now is that I'm going to try to use the Gauss theorem from the left. So what I do is that I write down this volume integral of the divergence. So this is the left-hand side of the Gaussian theorem. And I can reduce this as a triple integral. And I should, for the v parameter, I integrate from c to d, and then I integrate from a to b in the u parameter. And in the w parameter, I integrate, let's see, where is, you have that w goes from g1 to g2, so the lower limit here will be g1, and the upper limit will be g2. And then the integrand is simply the divergence, and this is v3 prime of, and then the parameter is w, and you integrate with respect to w. So this is the result. C, D, A, B. So I need an indefinite integral of this derivative here. And this is, of course, v3 of w. And you have to take it between the limits g1 of u comma v, and then d2 of u comma v, and then du dv. So I write here C, D, A, B. And then if I put in the upper limit, I get V3 of G2 of U comma V. And then minus V3 of G1 of U comma V du dv. So now I can split this these integrals into two. I do this C D A B and V3 of du dv, and then minus this integral here C D A B, and then I get V3 of G1 of U comma V. What I'm going to tell you now is that this is actually the flux integral of this vector field outside, out of the upper surface in the integral. But in order to do so, I shall need here the normal vector of that surface. So let me find this, because I call this, and I just indicate that this is not a unit normal vector, so I use capital N here, and I have the surface F2. And this will be the derivative of my parametric representation for this surface, and this will F1, and the derivative, it's a bit crowded here, will be with respect to U, and then with respect to V, and then I should make this cross product. So if you look at it, if you have F2 up here, then the first vector is with the derivative with respect to U is 1, 0, G2 prime of U. And then I should cross this with the same vector up here, differentiated with respect to V, and I get 0, 1, G2. I should have a U here, so it's a G2, and it's with respect to U, and here it's with respect to V, U, V. And when I make this cross product, I get minus for the first coordinate, and then minus G to U, or D to V for the second coordinate, but for the third coordinate I just get 1. 1 times 1 minus 0 times 0. So that is 1. So when I make the dot product between this normal vector and my vector field, I simply get the third component of the vector. And this is what I have here. So I can write this, let me just continue the writing here. I can write this as the integral from C to D, and then from A to B of my vector field times this normal vector, du dv. And quite similarly, I can write this integral here as a dot product of the vector field v, and then the normal vector to G1. But when you are talking about flux, you're looking at the outward normal vector to the surface. And this vector here is pointing into, it's simply here I can, this is N2 and this is N1. But when you're looking at the Gauss formulation here, you want an outward bound normal vector or outward pointing normal vector. So you will have to change the sign of that vector. But you have a minus sign here. So you get plus C to D and A to B of V, and then F1 du dV. So what you have now is that this is simply the flux of the vector field. This is by definition outside the top surface, F2. This is the flux of the vector field of the bottom surface. Now, for the 2 or the 4, say, bounding surfaces here, the normal vector is perpendicular to your vector field. So the dot product between these are 0. So you can add, say, some zeros to this, but the total thing is that you get the flux. You get the flux of V out of the boundary of your solid. So in this particular setting, you simply get that this volume integral is equal to this boundary integral. And the thing I like about this is that actually when you do this, when you go from here to here, then you use the fundamental theorem of calculus. Remember, I just write it here, that if you have the integral from A to B of the derivative of some function, then it is equal to the indefinite integral of this integrand, that is taking in the upper limit minus the indefinite integral taken in the lower limit. This is the fundamental. And you could say that this is quite similar to this, because here you have some kind of generalized derivative of your vector field, and you have an integration. You have an integration in 3 variables, that is a space integral, but you end up by having an integration in 2 variables, that you step 1 order of dimension down, and you have put, so to speak, the things out on the boundary, as you did here. So this is the similarity between them. But of course, if you have to do this more generally, then you have to, then it's a little bit more trouble to do so. But this is the general idea about it. I'll give you some examples after a break, and I think that we should resume at 10 minutes past.